All right, let's pick back up with our falling textbook on example 12. These make a pretty decent free response question. Someone's having fun with the Soma cubes back there. Okay, so the book hits the ground at a velocity of 160 feet per second. Let me go ahead and write the sentence. Just it's never too early to start preparing. Here's what how we're going to formulate our explanations. The instructions would say, explain what this means in the context of the book. So you always start with that introductory adverbial clause, which references the moment in time. So you'll say at t equals 5 seconds with units, comma. Again, you could say the book is falling at positive 160 feet, and then you write out per second. So if you're talking about the rate of change in position, you want to answer it in units of position, PER, time. So you're not just going to put feet diagonal second. You're going to write it out. And the falling part captures the negative. So it's a vector. We always interpret the sign as increasing, decreasing, rising, or falling in this case. And then we talk about the magnitude of that as a scalar, 160 in this case, feet per second. Now you can also, like I said, at t equals 5 seconds, the book hits the ground with 160 feet per second, or at 150 feet per second. What's the average velocity of the book during the duration of its free fall? Okay, do we need calculus for average velocity? Nope. Average velocity, remember, is your displacement, which is your net change in position over the elapsed time. So for us, it's going to be its position at the end, which was at 5 seconds, minus its position initially, which is 0 seconds, all over 5 minus 0. That is your DQ, right? Your difference quotient. And we need to make sure we show that. So what was the height at t equals 5? It was 0, right? Minus what was the height originally at 0? 400, all over 5 minus 0. So we get negative 80 feet per second. So the book, on average, was falling at 80 feet per second. Does that mean it was going 80 feet per second the whole time? No. Did it have to go 80 feet per second at least once? Yeah, that is getting into the mean value theorem. It started at 0, it ended at 160. It has to increase its velocities through a continuum, or in this case, decrease technically, right? If you look at the sign, it's going to pass through 80 on its way to 160. Yeah. But if you had a book that was dropped at 0 and actually fell the way gravity would, versus a book that when you dropped it was on cruise control for the 5 seconds and just fell at 80 feet per second the whole time, they would hit the ground at the same time. Wow. I saw that on Mythbusters. Yeah. How do you get a book to start going 80 feet per second at t equals 0? I don't know. Anyway, it's always interesting after lunch when we get the variety of mixed lunch smells, from the microwave. You'll smell it? No? Okay. What was the acceleration of the book in feet per second during its fall? Acceleration of the book. How do we find acceleration? It says during its fall. Is that instantaneous or average acceleration? I don't know. It's kind of a wide open question, right? I guess we could talk about the acceleration at any and all points during the fall, but let us start with maybe finding the acceleration equation. Oops. Our velocity equation was up there. Let me lasso that and bring it down. And now I can just bring the v part because I've labeled it as h prime. So if I bring that down, if I want to analyze the acceleration, let's find the instantaneous acceleration function. So that would be v prime of t, and I can rename that a of t if I so choose. And that's going to be negative 32, which, thank goodness, is a constant. So in any final numeric answer, make sure you put units. You can call that feet per second squared. That's fine. Now we'll write the sentence. The book falls, or the book, what does that mean? We could just say the book has negative 32 feet per second squared acceleration during its fall. Yeah, there you go. That's the better way to say it. Acceleration is the rate of change of velocity. So the book's velocity is decreasing, because it's a negative number, is decreasing by, and then again, because we're talking about the change of velocity, we're going to list it in velocity units, by positive 32 feet per second, that's a velocity unit, and then per second during its fall. And I just kind of violated my own rule. I didn't start with that adverbial clause. During its fall from t equals 0 to 5 seconds, the book's velocity is decreasing by 32 feet per second each second. So this word right here, if you don't want to use the word per again, you can use each second, every second, so on and so forth. All right? But we also understand acceleration. So you could say the book's had a constant acceleration in the downward direction of 32 feet per second squared during its fall. You'll often be asked to interpret acceleration both ways, or velocity both ways. Velocity is speed with the direction, but it also tells you how the position changes. All right? All right, so there's your brief introduction to the kinematics. We're going to have a whole lesson later on about particle motion from a derivative perspective. Then we'll look at particle motion again from an antiderivative perspective. And at the end of the year, we're going to be looking at particle motion for a third time. This is a BC only topic, using parametrics or vectors. Okay, we'll get into vector 2D movement. Okay, AB is just movement along a line, left, right, up, or down. But y'all are going to be able to get into a two-dimensional plane. All right. So now that we know the power rule, we can circumvent the alternate form. Remember, with the alternate form, allowed us to test for differentiability by checking the slopes and the y values at the same time. We don't need to do that anymore. So here it is. If f of x is that piecewise function, find the values of a and b so that the function is differentiable for all x. All right, so let's start with this. We need to make it differentiable for all x. So that means what has to happen? Yeah, number one, it's got to be continuous. If that doesn't work, it's not going to happen. And then number two, once it is continuous, then the slopes must be the same. The slopes have to be the same from both sides. If it's not continuous, it's game over. If it is continuous, we can then check the derivative from each side and see if they're the same. But this one is not checking for differentiability. This one's a little bit different. It's kind of like when we found the values of a and b to make the function continuous. Now we're forcing it to be differentiable. So let's go ahead and work on the continuity part. That's really the first thing we should check. Because if it's not continuous, it's not going to be differentiable. So using our three-step definition, boy, here we go. The limit as x goes to 1 from the left of f. My direct substitution is 3 minus 1, which is 2. And let's see, f of 1 is going to be the same as the limit as x goes to 1 from the right of f, because it's greater than or equal to. You plug in a 1 for x, and you get a plus b. Now, on the A-B test that we just took recently, let me kind of back up here. I saw a lot of this. They would have the limit there, and then they have ax squared plus bx, and then they would plug in their 1 and call it a plus b. Is that right? No. What's missing? On this piece here, we haven't evaluated it yet, right? So you can't say that variable expression is always equal to a plus b. That's only when x is 1. So if you still have variables and you have yet to evaluate it, you better have the limit in front of it if it's the limit, or f of a number in front of it if it's not. So that needs the limit in front. Now, if you wanted to do that, you can. Some people like writing down the actual expression of the piece that they're on. You don't have to do that. If you just know, it's f of x, I'm approaching from the right, I'm going to be using the bottom piece, I'll just plug right in and get a plus b. But if you like to write it like that first, that's fine. Just make sure you have the limit still, and now direct substitute, okay? Common errors. And so what has to happen then for this thing to be continuous? Yep, bless you. So we're kind of forcing it to be continuous. In order to be continuous, a plus b has to equal 2. Does that have a unique solution? No. 1 plus 1, 0 plus 2, 4 plus negative 2, lots of solutions. It's not unique. So we have two unknowns, we need two equations. Where in the heck are we going to get another equation from? From the slope equations, which is the derivative, right? So let's go ahead and find ourselves a piecewise derivative. That's legal. A piecewise derivative. What's the derivative of 3 minus x? negative 1, right? And that's going to be good to the left of 1. And then the derivative of the bottom piece by the power rule is 2ax to the first plus b. And that's going to be everywhere to the right of 1. Now notice what I didn't do there. I didn't say greater than or equal to 1. Why? As soon as I put the equal sign there, I'm saying f prime is defined at x equals 1, right? And do we know that yet? No, we are trying to make it exist. When you try to make something differentiable, you're trying to make the derivative exist at that point. It may be that we find the values of a and b that work, but it could be that there are no values of a and b that make it work, and you would be lying there if you defined f prime at x equals 1. So we hold off on the equal sign there, right? And we don't really need to check at, because that's what we're testing. We really only check from both sides. So now here's checking the slopes. I'll go ahead and check the slopes. Fresh white powder. Oh, let's go skiing. Okay, maybe in a few weeks, right, when the weather changes. The limit as x goes to 1 from the left of f prime of x is what? It's negative 1. And the limit as x goes to 1 from the right side of f prime of x is, you plug in a 1 for x, and you get 2a plus b. Now, in order to force the slopes to be equal to each other, there is no f prime of 1 here, like there is f of 1. When we check the bridge, there's no bridge with slopes. We just see if the slopes are merging. So 2a plus b has to equal negative 1. And again, we have one equation with two unknowns. There's not a unique solution. But now if we solve the system simultaneously, one with our left hand, one with our right hand, is that what simultaneously means? Not in this case, right? This means we just solved the system of equations. 2a plus b, I'm going to write them stacked over here, equals negative 1. So we put them together with an open brace, much like with the piecewise function. All right, so now we have our option of solving this by guess and check, elimination, substitution. I notice that my b's are the same coefficient, so I'm just going to do this. I'm just going to do the top one minus the bottom one. Or you could do bottom minus top, either way, which is probably what I'd actually do. But let's not do that. They're stacked this way. We're just going to have to mentally subtract. A minus 2a is negative a. B minus b is 0. 2 minus negative 1 is 2 plus 1, which is 3. So if negative a is positive 3, positive a is negative 3. Now go ahead and box that puppy up. Put air holes so the puppy can breathe. All right. Now how do we find a? We put it back into either one of these. I like the first one because it's more user-friendly. And so negative 3 plus b equals dose. And b must equal negative 5, right? I was rounding third. I was coming home. And I slid about 45 feet down the 90-yard base. And I came up about 15 feet short of home plate. That's going to make the blooper reel, right? That's not negative 5. Have I ever seen people do that at the end? Yeah, a lot of the times. A lot of times it's me. What does it end up being? Positive 5, right? Or they'll put negative 1 or something. Because mentally, you're kind of almost done. You see a negative 3, you see a positive 2. Hey, that's negative 1. So be careful. Slide at the right time, go all the way across home plate. To finish that analogy. Or run through the tape at the end of the race, right? I've run 2 marathons in my life, and I guess I'm proud of both of them because I hate running. But at the end of the Austin Marathon, in the last, I don't know, it was like in the last mile, you know, like when you could see the finish line, you just turn the corner, the Capitol's behind you, your name has, your little bib number has your name on it, and everyone's cheering your name. Run, Kevin, run. And I'm like, they know who I am, right? And you have that energy of anticipation of finally finishing a 4-hour race. And then there's a sign right there that says, free beer that way. And then right next to it, a sign that says, free finishing medals that way. And then another sign that says, free finishing T-shirts that way. And I'm like, man, people only run marathons so they can get the finisher's shirt and the medal, and who doesn't like beer? So there's so much temptation at the very end to just say, all right, I'm leaving the course, and then you go over there. But, you know, you got to run through the tape at the end of the race. But that's just a figure of speech because they don't hold tape up for every person that runs through, right? Just the first person. But you know what I mean, right? Yeah, yeah. Were there people that pulled off? Yeah, yeah. Okay. So that means that, how does that relate? Make sure that your mind is staying stuck to the task until you've got your answer, and don't just leave mentally to go on to the next idea and let your hand kind of finish up the work, because you're going to make careless mistakes. All right, so B is 5. So now that I have those values of A and B, can I come back up here and put an equal sign if I wanted to? Yeah, I could. Because I know it's defined. It's going to work. All right, any comment or question on that one? 130. All right, so let's do this one on your own. On your marker, set, go. It's kind of the same idea. Find the values of A and B so that the function is differentiable for all x. I'm going to kind of do it quietly with y'all if you're listening at home. Yeah, try it as well. No need to pause. Good. It's always good to see my answer appear somewhere else, because that means I did it right. My aunt's coming tomorrow. These types of questions could show up on either multiple choice or pre-response. Of course, on multiple choice, you wouldn't have to be so diligent with your notation. Hopefully, you would still be. Because, again, if you allow yourself to slide on notation when it doesn't really matter, you're liable to make careless mistakes by not having it there. And also, reinforcing that you don't need it. Maybe you slip on a free response and you don't write it, and you'll get deductions. But if this were like a multiple choice question, it would be kind of, maybe the question would say, what is the value of B so that the function is differentiable everywhere? Or it might say, you know, what is the value of A times B or A divided by B? And you just do something with them. But it says we want it to be differentiable for all x. So most of y'all jumped in right away and just started working at x equals -1, right? Why would we know to do that? Or do we even need to check anywhere else? No, not really, right? Because the top piece is a parabola and the bottom piece is a line. And here's what we know about polynomials. Not only are they continuous everywhere, but guess what? They are also differentiable everywhere. Yeah, polynomials are the smoothest curves you can work with, right? So we don't have to worry about any place other than where the graphs change from one to the other. Not only do they have to be at the same y value and be connected, they have to be merging in towards each other slope-wise so that it's a smooth transition. So again, I did my y values over here. I'm labeling it, free response kind of training, right? Either y values or continuity, label what you're doing. Here's the work where I'm doing that. Notice I did the 2 for 1 there on the top. You could do it still as road, bridge, road. But we do check f of -1, right? It's not a 2-step definition of continuity. It's a 3-step. And those both equal b minus 3, and then the limit from the right was -a plus b. So, again, a good transitional word. You could also do this, right? What is that? Y'all seen that little triad right there? What? Yeah, that's therefore, and sometimes you could use that as well. That kind of gives your paper kind of a nice scholarly look to it, right? I usually put a circle around it to make it stand out, because it can get lost pretty easily. And now it looks like Fred Flintstone's bowling ball or something like that. But anyway, so you set them equal to each other, and if you notice there, your b's cancel from both sides. So in this case, we get a equals 3. We have one of our values already without having to solve a system, but we don't know what b is. And if we plugged a back into the top, we'll still get nothing about b. So that's where then we take a piecewise derivative. And again, notice what I did at the top. Instead of saying less than or equal to -1, I just put less than 1. -1, sorry. So now I take the limits from each side of f prime, and by plugging in a -1 into the top, I get -2b. The bottom is a. So, or thus, or ergo is a good one. Ergo, if you want to use ergo, that's kind of nice. Ergo, consequently, or thus, you set those equal, you plug in, and you get b equals -3/2. Yeah, so it did work. If you notice what we did, excuse me, b is the coefficient of the x squared. So that parabola opens what, up or down? If b is negative, then the parabola opens down, and a is the slope of the line, which was positive, right? So we went from a parabola that opens down to a line that opens up, essentially. So how is that transition going to work? Yeah, if I do that, it's not going to work if I do that. Once I turn around and come back down on the parabola, any positive slope is going to make it not work. So yeah, you have it right there, Mr. Bird. It comes in like that, and as it turns to be a parabola, it just kind of becomes a line at some point. Yeah, because we're to the left of the vertex, which is where we have to be for that to be a differential. So I know it changes from parabola to a line, but it's going to be somewhere in there, right? It was so smooth, I couldn't tell where. Maybe, yeah, in there. Okay, cool. That was the last little piece of this section. So we have the power rule and we have the sine and cosine rule. Eventually, we're going to learn all 6 trig derivatives and all 6 inverse trig derivatives. So there's only a minute and a half left. We will probably do a little tiny quiz tomorrow over power rule, sine and cosine rules, and differentiability, okay? And then we'll start 2.4, which is the product rule and the quotient rule, okay? All righty. Enjoy the rest of your National Boyfriend Day.